Yeah, so I'm Tom, and I'm very excited to be talking to you all today about Allen. This is the GPU-based first level software trigger for LHCb, and I want to give a status update on Allen and talk about how we are preparing to take data, real physics data, early in run through of the LHC that's coming up. So the first thing you want to do when you're designing a trigger is you want to think of the kinds of signals you need to trigger on. So if you're at Atlas and CMS, the kinds of things you might be interested in are things like Higgs production or top production or electroweak bosons. And these processes will occur in run 3 at Atlas and CMS at a rate of about once every 10 seconds or so for a Higgs boson, up to a few kilohertz for electroweak boson production. And generally, these particles also produce high energy signatures in your detector that you can trigger on. So you might get high energy leptons or photons or jets, which you can then trigger on using just a signal from, say, your calorimetry system or your muon system. So in contrast, at LHCb, we're interested in processes like BB bar production and CC bar production because we want to study heavy flavor decays. And these processes will occur at rates exceeding 1 megahertz. So we really have to trigger on, we have this challenge of triggering efficiently on 1 megahertz signals. On top of that, BB bar and CC bar final states look a lot like underlying events in proton-proton collisions, so they're very difficult to trigger on using just single high energy signatures. And so you can see that in this plot on the left. This shows the performance, the hypothetical performance in run 3 of what we call a low-level hadron trigger. So this will select events just based on the presence of a single high energy hadron in the event, or a high PT hadron. And so we operated a hardware-based hadron trigger at a rate of about 1 megahertz in run 1 and 2. And if we do that again, so this is right in this area of the plot, way down in the lower left corner, we get efficiencies for hadronic charm decays of something like 5%. And hadronic B decays of something like 10%. So this is really very poor. So the signature you really want to trigger on for heavy flavor decays is a displaced decay. So the heavy flavor hadrons will travel some distance, and they will decay to some final state particles, some distance away from a primary vertex or a collision point. And so we want to look for the signature of a displaced heavy flavor decay. And this requires information from many detector systems working together. And so the solution we have come up with is to process every event at LHCb in run 3 in software. And this corresponds to an event rate of about 30 megahertz and a data rate of about 5 terabytes per second. And so we're really moving from triggering on single signals to what we call real-time analysis, where we are reconstructing, at least partially reconstructing decays and triggering on those reconstructed objects. So this is a layout of the LHCb data flow in run 3. The LHC bunch crossing rate is 40 megahertz, about 30 megahertz of that is non-empty. The detector will be read out. We'll read out every event, and this will be processed in this GPU-based trigger called HLT1. And this is what Allen is, and this is what I'll be focusing on today. Some of that data is then buffered and then used in real-time alignment and calibration, which can then be used to perform a full offline quality reconstruction in HLT2. And then this data is saved to disk for further processing. And so I'm the first LHCb talk of this conference, so I want to point out that there are a lot of talks this week focusing on various different parts of this data flow from the HLT1, real-time alignment, HLT2, and even some final analysis. So I encourage you to check all of those out. So I want to look back to where Alan was at the last Connecting the Dots in 2020. So this image on the left is my summary slide from when I talked about Alan at Connecting the Dots 2020. And so back then, Alan was a prototype implementation of LHCb's first stage software trigger on GPUs. And we had some promising throughput. So if you look at the RTX 2080 Ti, which we use as sort of a benchmark card, we were getting throughputs of around 70 kilohertz. And so this meant we could hope to process the full LHC event rate with about 400 cards, and we have something like 500 slots. So this is great. And we also have some headroom for additional features. So this looked really promising, but we were still waiting for the final hardware decision from LHCb. So maybe the biggest change since 2020 is that Alan has now been selected as LHCb's actual first level software trigger for Run 3. And the decision process is documented in this paper I've linked at the top. So LHCb produced viable triggers based on both CPUs and GPUs. And so the decision came down to a detailed cost-benefit analysis of the full data acquisition systems you could create using each of these technologies. So the CPU based system I've sketched out on the left, you have PP collisions producing about 5 terabytes per second of data that then go to these event builder nodes that package that data into events, and then that's shipped off to a CPU farm where the software triggers run. For the GPU-based system, we can place the GPUs in these event builder nodes, and we can filter data directly on the event builder nodes, taking this data rate down from 5 terabytes per second to about 200 gigabytes per second before going to a CPU farm for further processing. And so what this does is we save a ton of money on networking at this step, and we save a lot of money on processors at this step because GPUs end up being a lot cheaper than CPUs. So then what we end up doing is we get a lot more physics for our money within the GPU case. And so the final verdict was that a GPU-based software trigger will help LHCb expand its physics reach in Run 3 and beyond. So this is the basic job of Alan. So Alan is the GPU-based first-level software trigger, so HLT1 for LHCb. So Alan's basic job is to reconstruct tracks and look for displaced heavy flavor decays. So what that means is we reconstruct data from the vertex locator, or VALO, this upstream tracker, the UT, and this scintillating fiber tracker, or the SciFi. And then we can better select data if we can identify muons. So we decode and reconstruct data from the muon stations. So we decode the data, cluster it into hits, build tracks, identify the collision points, or primary vertices, and then match those tracks to muon hits. And then we can use all of the reconstructed tracks to create secondary vertices and try to find displaced heavy flavor decays and select those. So this is the basic job that Alan was designed to do. And Alan works as a standalone application or as part of LHCb's software stack. And it can be compiled for CPU and GPU with CUDA for NVIDIA cards or HIP for AMD cards. And if you want to see a detailed overview of this tracking sequence, there will be a nice talk by Alessandro later in the week. So one of the things that really excited us about Alan was that we had this throughput headroom. So we could do more than just this baseline task of reconstructing tracks. And so this slide on the left is one of the slides from my talk 2 years ago, where I talked about how excited we were at the possibility that we had enough throughput headroom to do ecal reconstruction and electron identification. So LHCb has a lot of interesting physics it can do with electrons, for example, tests of lepton flavor universality. or searches for BSM physics like dark photons decaying to electron pairs. And so being able to actually trigger on identified electrons in HLT1 would really help strengthen these physics programs. And so now this has been implemented in ALAN, and as proof of this, here is a map from a heat map of the energy deposits in the eCal from some cosmic data that was selected using ALAN, and so you can see that we are actually able to reconstruct energy deposits and select them. So we have implemented eCal decoding, eCal clustering, matching tracks to those clusters to identify electrons. And we can even recover Bremsstrahlung losses from those electrons. And so we have a full electron reconstruction working in ALAN. Another thing we're interested in is using robust machine learning in our heavy flavor selections. So one problem you run into when you try to select a displaced vertex or a displaced decay using a neural network is that when you get out to very large decay times, you don't have very much signal and you have some background from detector interactions. And so our interactions with material that produce some very displaced vertex. And so you get some, if you use an unconstrained neural network, for example, you might get a lifetime response that looks something like this, where your efficiency of your classifier increases and then starts to fall off at very large lifetimes. But we as physicists know that we actually want to keep this data. There's not that much background here, and we want to select efficiently. We want to select efficiently on this signal. And so this paper here that I've linked at the top of this slide details the development of provably monotonic machine learning architectures. So this you can constrain your algorithm to have a monotonic response in some variables. So this middle plot shows the response of a monotonic BDT, a BDT that's constrained to have a monotonic response in lifetime. And so you can see there's this nice increase in efficiency, and then it plateaus instead of falling off. In addition to that, we want to run these in real time under real data taking conditions. So the data taking conditions might be unstable and they might fluctuate. So we can further constrain the maximum gradient of this response function. And this is what is called this monotonic Lipschitz neural network. And this is what's shown on the right. And so neural networks are very fast to evaluate. These small neural networks that we're using are very fast to evaluate. And so this monotonic Lipschitz neural network has now been implemented in ALAN's inclusive heavy flavor selection. So this is really sort of state-of-the-art machine learning research that is being used online to select heavy flavor decays with ALAN. So we've added all these new features in the past couple of years, but still ALAN has gotten a lot faster. So this is our latest official throughput plot from 2021. And so you can see, I mentioned we were getting a throughput of about 70 kilohertz on the RTX 2080 Ti in 2020, and now we're up to something like 140 or a little over that. This is before things like eCal decoding eCal reconstruction were added. So once you add these new features, ALAN is still about 50% faster than it was in 2020. So this is really a great improvement. So now we can hope to process the full LHC event rate with something like 200 cards instead of 400 cards. And so this either saves us a lot of money or allows us even more headroom to do even more cool things and expand the sorts of signals we can trigger on. In addition to this, we have achieved competitive throughput on this AMD MI100 GPU. So this is an AMD card, and we get very nice throughput here, and it's completely viable for our HLT1. And so this means we have two potential vendors we can use for GPUs. So this is important for getting a competitive tender process. So we've developed this trigger, and now it has to face reality and face the realities of collecting data. So one challenge we're dealing with is that we don't expect our upstream tracker to be in place until December. And so the UT provides it sits in an area with some residual magnetic field. So it gives us a first estimate of the particle's momentum and also the charge. So if we have no UT, then we have to create tracking algorithms that can reconstruct tracks without momentum information and without charge information. And so we want to do this while sacrificing as little throughput as possible and as little physics performance as possible. And so I want to point out that there will be 3 talks this week by Andre, Alessandro, and Bridge that will all touch on how this challenge is being approached and how we are going to reconstruct tracks without this information and not lose significant physics reach. So LHCb will collect data not just in a PP mode, but we will also collect data in fixed target mode using what is called the SMOG system. So this is the system for measuring the overlap with gas. The SMOG system was originally developed for precision luminosity measurements, but it's since become has a physics program of its own. So this plot on the left shows the distribution of primary vertices for PP data, which is this big lump on the right, and proton gas data, which is this lump on the left. And so LHCb will collect data in the proton-proton and proton-gas modes simultaneously. So LHCb Alan needs to be able to reconstruct data in both the PP and P-gas mode without loss of physics performance. And so we've been able to do this. This plot shows the Velo track reconstruction for different data taking scenarios. And you see we don't lose any efficiency by going from just PP alone to proton-proton plus proton helium and proton-proton plus proton argon. And then on the horizon, we're also getting ready to take lead-lead data. So this will happen in November of this year. And so one issue we have is that as we get to very high detector occupancies, the sci-fi starts to saturate. So this plot shows the tracking efficiency in lead-lead events as a function of the number of hits in the sci-fi detector. And so what you can see is that this efficiency really starts to fall off, and the sci-fi is saturated by about 30,000 hits. And this is an issue because most lead-lead collisions will produce more than 30,000 hits in the sci-fi detector. So this means we have to rethink our trigger strategy in Allen, and we have to come up with a new way of selecting data in lead-lead, and this is something we're currently working on. So throughout May, Allen has been commissioning using Cosmics. So it's been fully integrated into the data acquisition system, and to start, we're just testing by selecting eCal clusters with a minimum ADC count. So this is the plot of the heat map of the eCal energy depositions on the left, and then this plot on the right shows the bunch crossing IDs we select. So we randomly read out the detector at a rate of 1 megahertz, and we end up selecting Cosmics at a rate of a few kilohertz. And you can see that these selections are sort of randomly distributed across bunch crossing IDs, which is what you would expect for cosmic rays. So we've been successfully triggering on Cosmics, and we've had nice interplay between Allen and the eCal. And then as a very exciting step forward, just this weekend, Alan collected its first data with stable beams. So this image on the left is a screenshot of the dashboard that the shifter will see in the control room. You can see that this was a screenshot taken on May 29th, 2022. So this was the first stable beams that Alan triggered on, and I want to point out these rateometers here. And so you can see that there's an input rate into Alan of about 5 megahertz, and Alan is selecting data at a little over 50 kilohertz. And then on the right, this shows the bunch crossing IDs of selected events. And so we are actually selecting particular bunch crossings. So this indicates that we are really selecting PP collisions. Alan is successfully triggering on PP collisions. So this is a huge step forward for Alan and is very exciting. This marks the transition from a prototype to a real functioning software trigger. So some final thoughts. In the last 2 years, Alan has gotten a lot faster, even as we've added more features, and there are more features we want to add. And so I hope there are a lot more exciting things we can do with Alan in the future. And we've gone from a prototype to a real functioning software trigger. We are selecting PP data, and run 3 is just getting started. And so I'm sure as we go on, we'll uncover more challenges, but I think it's going to be a lot of fun and a very exciting time to work on this project. So in conclusion, I want to compare the past, connecting the dots 2020, to the present. This is a tweet by the LHCb experiment announcing that Alan has selected its first PP data. So I encourage you to all go follow the LHCb experiment on Twitter. So thank you very much.
I saw there were some questions coming in the question. You want to read it?
Sure. So the question was, why do you have 2 HLTs and why is the second one still on CPU?
So that's a good question. We have 2 HLTs because on one of them we can do this first is a lot faster and takes a lot less time and only does a partial detector reconstruction, and then the second one does a full detector reconstruction. And so this is, sorry.
Go ahead.
Oh, okay. So this second stage does a full detector reconstruction with things like particle ID, so information from the ring imaging Cherenkov detectors, the HCal, things that we don't have time to do online, at least yet. And the question for why it's still on CPUs is, I think there are plans, or at least we're studying, eventually not having it on CPUs. So eventually having a hybrid GPU, CPU, HLT2 a lot further down the line. But this is sort of one step at a time. So eventually this could, a lot of this reconstruction could be done on GPUs.
Okay, thanks. Any questions in the room? Professor Sandy and Marcus.
Tom, very nice. Thank you to see this update. I think that's a real great story. You must have some interest as a collaboration that the GPU farm is being used and not idle when you're not taking data, I suppose. So have you discussed how to explore them first on the analysis side, for instance, for ML training or inference, and second, did the Geant community, which is restarting the GPU demonstrator, did they contact you?
So I can't speak on Geant specifically, and I don't know about that. I know there's a lot of discussion on how to use these GPUs while we're not taking data. How to use them for things like machine learning training, how to have use the GPU farm as a service. And I'm not exactly sure what the status of that is right now, because I think most effort right now is getting ready to take actual data, but this is definitely something that people are discussing and studying. But I can't speak. I don't know. I don't know what the status is.
I was even interested if they reached out to you.
Yeah, I don't know. They didn't reach out to me. they would have. Yeah.
Okay, so Marcus.
Yeah.
Well, just one thing. As I don't know most of you, so can you state your name before asking the question? Also for the.
Yeah. So Marcus. Thanks very much for this very nice update on all this impressive things you've shown us. One of the things which came to my mind is you said that you needed much less GPU cards. Did you run into any trouble when purchasing the cards? Because I mean the GPU prices recently weren't necessarily cheap, right? Or was that protected by in some form that you didn't run into purchasing problems when you got the phone?
Yeah, so I don't know exactly how the tender process worked. I wasn't involved in the actual purchasing.
Okay.
I think there was a lot of negotiation, and it was very important that we had two vendors that we were able to look at both AMD and NVIDIA cards, but I think it's safe to say we got a good deal from NVIDIA.
And the other question I had is, you mentioned in later events your sci-fi tracker saturates, which was new to me. Since you don't have the upstream tracker, I mean, how's the reconstruction strategy in general in such a situation? And I mean, isn't that a major problem for the LED program?
So it is, but so LED is, or LHCb has taken LED data before, and it's had this issue before, where we have saturation in various detectors. And so typically what we've done is we've just studied not very central LED events, relatively peripheral LED events, down to a centrality of something like 65% centrality, which is not super high occupancy, and that's somewhere. I think that corresponds to somewhere around here on this plot. So there's. I think the strategy going forward for Alan will be to use Alan to select events that look like, so not only will we be selecting LED events, we'll be doing LED plus LED gas at the same time, similar to this. So we'll have LED argon events going at the same time. And so Alan needs to, the primary goal of Alan is to be able to flag these LED argon events and LED events to be passed on to HLT2, and to maybe scale down these super central LED events so that we don't waste a ton of time on HLT2 processing them. But there are also some other interesting things we could do in Alan. For example, do something like Velo muon tracking, which is something we're looking into, where we can reconstruct muons just using a Velo segment, just using a muon segment. And just bypass the sci-fi entirely and hopefully not run into any saturation there. But this is very preliminary, something that is still sort of a work in progress.
Okay, so there was last.
Hi Tom, this is Paolo. Marcus almost asked a question I wanted to ask, so I'll ask a similar one. How did you pick between the various like 6 or 7 GPUs that you tested? I mean, they had many of them had essentially very close performance. So was it Swiss francs? Was it megawatts? Was it rack space? What was it in the end of it?
Yeah, I think it was a combination of all these things. I think the absolute best bang for your buck comes when you use a gaming card. So we don't necessarily need all of the fancy things that a scientific GPU gives you. So So we would get the best bang for our buck from something like an RTX 2080 Ti or the 3090. But there's some licensing issues with this. So we have to get a card with the right licensing so we can actually collect scientific data with it. And this is a whole part of the tendering process with NVIDIA. And so somehow all of these considerations together, we ended up with the RTX A5000.
Thanks. Yeah. Yes, another question.
Yeah. So when it comes to porting stuff between NVIDIA and AMD GPUs at the core level using HIP, how efficient is it? Like, essentially, can I get away writing CUDA code and compiling it on HIP and getting it to run directly on AMD GPUs? Because we are also facing similar issues. We think we are kind of mental artists. Yeah,
so it's definitely hard, right? It's definitely a difficult thing. But so we developed sort of our own sort of performance portability layer. So we have we have code that we can write just in code that looks like CUDA, and then we can compile for CPU or compile it for HIP using some compiler flags that change the definitions of some symbols. But yeah, it's a lot of work. You have to develop your own performance portability layer. That's not easy. And also these different languages support different features, different things. If you want to do things like the object-oriented programming is not very well supported on GPUs, maybe for good reason, but there's sometimes things you want to do that are sort of object-oriented. And CUDA and HIP handle these things differently and allow you to do different things. So you definitely have to keep in mind through the whole development process that you want your code to run on both of these architectures. Does that answer your question?
Yes. I see there is a lot of interest. We still have some buffer. So should we have allow for a last question, or should we?
Is there anyone with a question on Zoom? Just raise your hand if you.
Yeah, we didn't mention, so people that have a question, raise your hand and we'll see you. Okay, so let's go.
I'm Alexis Valier from L20. Thanks for this nice talk. I was wondering, you mentioned that over the past 2 years, Allen got a lot faster, and with adding more features on it. So it sounds a bit magical. So could you elaborate a bit more? What were the main breakthrough in the getting this fast?
Yeah, so there are a lot of little optimizations in various algorithms. The things like, especially the Velo tracking, some things have been sped up there. One thing that was very important was we sort of changed the way we looked at how to optimize things. So we went from you can't. It's hard to optimize a GPU. A GPU program that has many different algorithms and runs many of those algorithms in parallel on multiple streams just by looking at the throughput of individual steps. And so we went from looking at the throughput of individual steps to looking at how to maximize GPU occupancy at all times. And so this allowed us to get some big speed ups, but it was really things like 10% on one algorithm, 10% on another algorithm that built up over time, along with simple things like optimizing block dimensions and stuff. It's a really slow 2-year process of accumulating speed ups.
One small. Very last. I'm sorry, it's Andy again. Have you seen, because we have seen this lately, have you seen also speed ups by different compilers? I mean, we have seen up to 10% by not using CUDA compiler, but Clang directly, and suddenly the code got faster.
Yeah, so we've studied CUDA Clang, and doing things like playing with compiler options leads to speed ups. That's some of this speed up.
And differences, of course, and suddenly uncertainty systematic uncertainty, which we would call compiler uncertainty.
Yeah, exactly. There's some throughput uncertainty, so you have to have a very specific compiler recipe to get the absolute best throughput out of Allen, and that's something we're constantly sort of optimizing.
Okay, I think we have to move forward. So let's thank Thomas again.